Okay, second lecture for chapter 18. We left off talking about preconditions, which are the same as we've talked about before with anything dealing with proportions. The individual data values that we've taken, the yeses and nos or whatever, must be independent of each other. And they must be randomly collected. And the sample must not be too big. That's a 10% condition. You can't have more than 10% of the population, otherwise the standard error is no good. And NP and NQ must be greater than or equal to 10. At least 10 successes and 10 failures. If all of these preconditions are met, then the normal model can be used to describe the sampling distribution of the sample statistic. Okay, so now here we have a complete restatement of the one proportion Z interval, okay, or the confidence interval. That's the name of the test, one proportion Z interval, where we're using Z-scores distributed according to the normal model to make our confidence interval. So the confidence interval equals p hat, the sample statistic, plus or minus the margin of error. The margin of error equals Z star times the standard error of p hat, and the standard error of p hat equals the square root of p hat q hat over n. So to put it all together, come on pen, let's go, there we go. Confidence interval equals p hat plus or minus Z star times the square root of p hat q hat over n. Let me clean up my little star here. Doesn't look so good. Z star. And Z star is the level, the Z score. Wow, learn how to write. Z star is the number of standard errors that correspond to our level of confidence, that correspond to the desired level of confidence. And the most common ones are 90%, 95%, 98%, and 99%. Okay, now I'm going to stop the thing here for a second and show you how you find the Z-scores that go along with these levels of confidence in your book. So in your books, if you go to the back, Appendix F in your books, give you a second to look at it. Now it looks like this. Now, the first appendix or the first table, Appendix F is tables. Okay, the first table is random digits. The second table is areas under the Z-score for various Z-scores. We usually don't use this, we just use normal CDF. Okay. The next table in Appendix F is the continuation of the Z tables. Okay. And notice that page A84. Now, this page, the T table, table T, okay, is the one you want to go to, page A84. And you want to go down, scroll down to the bottom. Okay, and they have confidence levels. So, for an 80% confidence level, Z star is 1.282. So in other words, 1.282 standard errors to the left and 1.282 standard errors to the right will cover 80% of the area under the curve, thereby giving you an 80% confidence level. 90% is 1.645. So if you do 80%, 10% is left in each tail. 80% in the middle, 10% in each tail. 90%, 5% is left in each tail. 5 on the right, 5 on the left for 10%, leaving 90% in the middle. And 1.645 is the number of standard errors to the right and to the left that covers 90% of the area under the curve, under the normal model. So the Z star for 90% confidence is 1.645. For 95%, we were thinking of this as 2 standard deviations, but in actuality, it's exactly 1.96. So the Z star for 95% confidence is 1.96. The Z star for 98% confidence is 2.326, and the Z star for 99% is 2.576. Now, you can find these numbers on the calculator by using inverse norm, but it's kind of a pain because you got to do a little bit of thinking, and maybe if you're in a test or something, that's hard to do. This page is always available during the test. You can always just quick flip to this page and look up these numbers in every quiz and every assessment that you have in which you have to calculate confidence intervals. This will always be available to you. In other words, this is always available to you when you have assessments. So, but if you were going to use the calculator to calculate 80% confidence interval, remember you want to leave 10% in the tail on each side, so that had to be inverse norm 0.9, leaving 10% on the right, and then therefore 10% on the left. If you wanted to use your calculator to find the Z star for 90% confidence, you would do inverse norm 0.95. If you wanted to do it for 1.96, for 95% confidence, then you would do inverse norm 0.975. And for 98%, it'd be inverse norm 0.99. And for 99%, it'd be inverse norm 0.95. Now, if you're comfortable with doing that, then do that. And use that to get your Z stars. Otherwise, they're in the bottom of the table T, A84. And like I said, they'll always be available on the test. I'll make sure you always know where they are. Okay, so back to what we were working on right here in the book, which is right here. Okay, so now let's move on. Step-by-step example, very, very important. Okay, so let's work through this. October 2010, the Gallup poll asked 510. Okay, so we're going to start, as you're going along here, you should start ticking off information in your mind to answer this question, to what's important. Gallup poll. Okay, what does that mean? Gallup poll is one of our accepted sources of authoritative. It's my wife laughing at me. Authoritative information, polls and such. So you see the word Gallup, everything's cool. All right, so they randomly asked 510 adults the question, generally speaking, do you believe the death penalty is applied fairly or unfairly in this country? Of these, 58% answered fairly, 36% said unfairly, and 7% said they don't know. Percentages add up to 101% due to rounding. Okay, so fairly, unfairly, and don't know. By the way, we're going to do an interesting a test on this later on in about a week or so. From this survey, what can we conclude about the opinions of all adults? All right, well, to answer this question, we'll build a confidence interval. All right, so we're going to make a confidence interval for all U.S. adults, within which we want to have a certain level of confidence that that the true proportion of adults the true proportion of adults who think that the death penalty is applied fairly will be contained. All right, on the left, this 2-column page here is what you must do. Thinking, etc. Think, show, tell. And on the right is what you actually do, what you have to provide in your answer. So, think, plan, state the problem in the W's. Identify the parameter you wish to estimate. Identify the population about which you wish to make estimates. Choose and state a confidence level. Okay, so you're going to choose 95% confidence. That's pretty common. I want to find an interval is likely with 95% confidence to contain the true proportion P, population parameter, of U.S. adults who think the death penalty is applied fairly. I have a random sample of 510 U.S. adults. Okay, that paragraph is extremely important. Not just, because people expect you to write it or whatever, but that's true, but because now you know what you are trying to do. Okay, you know your population, you know the population parameter you're concerned with, and you know the level of confidence that you're trying to establish with the sample statistic taken from your random sample of 510 U.S. adults. Okay, now you got to go through the preconditions. Why? Because you want to establish that it's legitimate for you to use the normal model to describe the distribution of your sample statistic, the sampling distribution of your sample statistic. Okay, it's Gallup. They drew a random sample. You must state that, okay? I can be confident the respondents are independent. 10% condition. Success and failure. Note, they show the work. 510 times 58, 410 times 0.42. Okay, the conditions are satisfied, so I can use a normal model to find a 1 proportion Z interval. Notice, you're going to use Z-scores. You need the normal model. Okay, this statement, very, very, very important. Everything here, you got to show. Okay, next page, I believe. Okay, now you're going to show the mechanics. Okay, n equals 510, p hat equals 0.58. So the standard error of p hat, you're going to show the work for calculating the standard error. You're not just going to write down a number. You got to show all of this, okay? Because the sampling model is normal for a 95% confidence interval. The critical value Z star is 1.96. Let's look back at our chart here. Go back down to the bottom, okay? I want a 95% level of confidence, so the Z star, the number of standard errors I go to the right, the number of standard errors I go to the left, it's going to be 1.96. Okay, and let's go back to where we were. All right. So the margin of error. Margin of error equals Z star times the standard error of p hat. 1.96 times 0.022. We calculated that up here, okay, which is 0.043. Okay, so the 95% confidence interval is 0.58 plus or minus 0.043, or 0.537, comma 0.623. I am 95% confidence, level of confidence, that between 53.7 and 62.3% of all U.S. adults think that the death penalty is applied fairly. So now you're gonna write your conclusion. Note everything you did on the left. Okay. Confidence interval is settled at the sample proportion. The width seems reasonable for a sample of 500. Okay. So everything on the right here is stuff that you had to do. All right. Finding confidence intervals on the calculator. That will come as no surprise to you. You can do all this. Okay. Stat test. All right. All right. Now, let's just go through this real quick. Let's go through. Okay. Where's my calculator? Right here. Start it up. Okay, so we're going to do this for the diseased C fans. Okay, we had 104 and 54. So we want to find the confidence interval. Okay, now we're going to go to stat and then tests. Okay, now we want a one proportion z-test. See, they're going on here. One proportion z-test, so arrow down. One proportion z-test. I hit enter. Okay, now, I'm sorry. We'll do this. We're going to do this later. I got tests on my mind here. Here, stat, test, one proportion z interval. Sorry, guys. I can't even read the directions. There we go. One proportion z interval. Okay, so x is 54, and n is 104. Okay, n is the sample size, x is the number of successes. Okay, note that the confidence level it defaults to is 95%. I hit enter. And there's the confidence interval, and it gives you p hat. It's nice of you. And n. Okay. Now, all of this is really easy to do. I mean, the arithmetic that was involved is trivial. The hard part is all the other stuff that the calculator doesn't do. The thinking, the explaining, all of that stuff. So, don't think by any means that this somehow eliminates all that other work. It does not. It's just a little, it actually just helps, it's just a little bit of a help. Okay. Now, choosing your sample size. Oops. This is important. Okay. Now, suppose candidate is planning a poll, wants to estimate voter supply. Okay, we want 90. Here. Now we're going to do some. Here's where we get to do some math. So you guys that like math, you're going to be happy. Those of you that don't like math, you need to practice. Okay? Now, suppose we want the margin of error it to be 0.03. So in other words, we don't want the margin of error to be plus or more than 3 percentage places to the right or 3 percentage places to the left of p hat. Otherwise, it's too uncertain, where exactly p is. Okay? So the margin of error equals z star times the square root of p hat q hat over n. Okay? Now, we know what z star is, and we know what the margin of error is that we want. So let's start filling in stuff that we know. 0.03 equals 1.96. Now, we haven't taken the poll yet. So in terms of calculating, this stupid thing, in terms of calculating how big the sample size needs to be, we're going to take the worst case scenario, which is that our p hat is 0.5. That way we know that our sample won't be too small if p hat ends up being actually close to 0.5. See, we're doing this before we do our poll. Why? Because we want to have a confidence level that's small enough so we have a pretty good idea, a confidence interval that's small enough so we have a pretty good idea of where p is. So if our sample, the smaller the sample size is, okay, the smaller that n is, the bigger that this number is going to be. There's an inverse relationship between the size of n and the size of the margin of error, right? Because n is in the denominator. Okay, so now we just have to solve for n. And from this point on, it's just a pretty straightforward algebra problem. Okay, so we're going to divide both sides. I don't know how I'm going to follow how they do it in the book. I'll just do it this way. Oh, they want to multiply. Okay, let's do it their way. Let's do it their way. Maybe you'll like that way better. Okay, let's use the property of exponents to do something here. I'm just going to show you kind of what they're leaving out. You can do this in your head. Okay, 0.03 equals 1.96 times, this is the property of roots, 0.5 times 0.5, come on guys, divided by the square root of n. Okay, so if you have one radical, you have a fraction underneath one radical, you can break that radical up into one radical being divided by another, as long as they're the same index, or the same root, and they're both square roots. Okay, so now all I have to do is multiply both sides by the square root of n. I get the variable over here out of the denominator. Remember, I'm trying to find n. So now I'm going to have the square root of n times 0.03 equals 1.96 times the square root of 5 times the square root of 5, which is simply the square root of 5 squared is 0.5. I'm sorry, square root of 0.5 squared is 0.5. So let's simply write this as 0.5. Okay, the square root of 0.5 times 0.5 is going to be 0.5. All right, now we divide both sides by 0.03. Remember, we want to isolate n. So we're going to have 1.96 times 0.05 divided by 0.03. And now, what's the inverse operation for square root? It's power. Okay, so we're taking the square root. So we square the square root of n equals 1.96 times 0.05 divided by 0.03. So n is going to approximately equal oh, I forgot to square this. Square both sides. Okay, so let me put this in parenthesis. 1.96 times 0.05 divided by 0.03, close parenthesis, squared, equals I made a mistake here. I got to figure out what it is, because it looks like I did exactly what I should have. But I made my mistake right here. You probably saw it. It's 0.5. I don't know why I went from 0.5 to 0.05. Okay. And let me fix this. Okay, there we go. Now I knew I was wrong, not because I looked at the book, but because I knew the sample size of 10 had to be wrong. So then right away I started looking around, what did I do wrong? And then as I was going down doing my math, I inserted a 0 there. Okay, so now what you have to do here, the answer is 1067.1. Don't round down. You have to round up. If you round down, you may not have enough people to reach that level of confidence. So I'm going to round up to 1068. That portion of one person, that could make the difference. Okay. Now, to be safe, we round up and conclude. Let's do another one. Okay? I'll see if I can avoid making math errors this time. You can follow along this one, but I strongly suggest you follow along and do this. This is the kind of question that comes up on multiple choices. Also, I don't know if you remember, one of the points that Whelan made in his book about what professional statisticians often do wrong is they fail to calculate the proper sample size. So this is, in fact, a very important calculation to do. All right, so we had the Yale George Mason poll. Let's go through this for example. Estimated 40% of all voters believe that scientists disagree about whether global warming exists. And that had a margin of error of plus or minus 3%. So they were 95% confident that between 37% and 43% that the true proportion of voters who disagree about whether global warming, let me get the statistic right here, between 37%, we are 95% confident that the true proportion of voters who believe that scientists disagree about whether global warming exists is between 37% and 43%. Okay, now suppose an environmental group planning a follow-up survey of voters' opinions on global warming wants to determine a 95% confidence interval with a margin of error of no more than plus or minus 2%. Okay, now the margin of error, as they write here, equals z star times the square root of p hat q hat over n. Now, we know the margin of error we want. The z star is not changing. We're not changing the level of confidence, but by increasing the sample size, we are going to make the confidence interval narrower. Okay? It's going to be narrower than the one we just calculated. It's going to be narrower by 2%, 1% on the left, 1% on the right. So 0.02 equals, and it was 95%, 1.96 times, now the p hat that they got was 0.4, so it's 0.4 times 0.6. Now this time, they're going to use the p hat from the previous poll to estimate the sample size for the next poll. So they're not going to use the worst case scenario. They're not going to use 0.5 times 0.5, which would cause them to come up with the greatest n in order to meet their goal of 0.02. The reason for that is they're probably trying to keep costs down. So they're hoping that the previous p hat will provide a pretty good starting place to estimate the sample size for a narrower margin of error. So now we're going to go through the same process we went through before. 0.02 equals 1.96 times the square root of 0.4 times 0.6 over the square root of n. Now, you don't want to calculate that yet. You're going to do everything at the end to avoid cascading rounding errors, because all these calculations are going to affect each other down the road. So we don't want to calculate that yet. So now we're going to have the square root of n times 0.02 equals 1.96 times the square root of 0.4 times 0.6. Now we're going to divide both sides by 0.02, cancel out the 0.02 on the left, and we have the square root of n equals 1.9, see, look at I dropped the 96 here. 1.96 times the square root of 0.4 times 0.6 divided by 0.02, And now we're going to square both sides. And n is going to equal 1.96 times the square root of 0.4 times 0.6 divided by 0.02 squared. Okay, now let's see if I can get this in the calculator right for a change. So I'm going to clear this, and I'm going to do open parenthesis 1.96 times the square root of 0.4 times 0.6 close parenthesis divided by 0.02 close parenthesis squared. Okay, let me double check that. 1.96 times the square root of 0.4 times 0.6 close parenthesis for the square root function divided by 0.02. Okay, close parenthesis for the whole expression that I want to square. I hit enter, and I get a sample size of 2304.96. So n is going to be approximately equal to 2305. So that's how big my sample size has to be to lower the confidence interval by 1 point on each side. So to go from a margin of error of 0.03 to 0.02, I've got to increase the sample size from, what was it before? What was the sample size before? It doesn't say. Okay, anyway, I got to lower it, I got to increase it to 2305. Okay, moving on. So they talk about to cut the standard error and that's the margin error in half, we must quadruple the sample size. Okay, that's because we're taking the square root. And they talk about the pros and cons here of how big the margin of error should be. And it's obviously going to depend. But you've got limits of time and money. So that all of that has to be taken in consideration. All right, so sample size revisited. A credit card company is about to send out a mailing to test the market for a new credit card. From the sample, I want to make sure this thing is running. Okay. From that sample, I want to estimate the true proportion of people who will sign up for the card nationwide. A pilot study suggests that about 1/2 of 1%, 0.5% of the people receiving the card will accept it. To be within 1/10 of a percentage point of the true rate with 95% confidence, how big does the test mailing have to be? Okay, so let's look at this math here. Let's review what we know. Okay. The margin of error equals the level of Z star. That's the number of standard deviations that corresponds to our level of confidence. In this case, our level of confidence is 95%. So Z star is going to be 1.96 times the standard error, the square root of P hat Q hat over N. Okay, so we want the margin of error to be 0.001, right? And the Z star is 1.96. And what did they say? P hat, the percentage of successes is 1/2 of 1%. So it's 0.0, not 0.05, but 0.005, which means that Q hat is 0.995. 1 minus p hat. Okay, and now we're going to find n. Okay, it's really important that you, if you're feeling at all uncertain about this mathematical operation, it's really important that you go through it. And we're just going to repeat. Now they do this a little bit differently here. What do they do? They square both sides first. Let's just go through the way. I want to repeat the way we've been doing it. Okay, I don't know why they're introducing a different method. Anyway, so 0.001 equals 1.96 times the square root of 0.005 times 0.995 over the square root of n. And if we follow the same procedure, the square root of n times 0.001, multiply both sides by the square root of n, is going to equal 1.96 times the square root of 0.005 times 0.995. Square root of n equals 1.96 times the square root of 0.005, 0.995 divided by 0.001, and n equals okay, let's see if we come up with the same answer. Open parenthesis, that's what we're doing right here. 1.96 times the square root of 0.005 times 0.995, close parenthesis for the square root, divided by 0.001, close parenthesis, squared. 1.96 times. Oh, they used 0.05. They used 0.5. Let me go back to this. Okay, so we got the right answer. We got the same answer that they got here. And this would obviously be rounded up. So n equals, the sample size we need to have would be 19,112 to make sure that we were within a margin of error of 0.001. That's really a small margin of error. Okay, now if they decide instead to use the worst case scenario of 0.5, notice how much bigger it has to be. Why? Because 0.5 is so much bigger as an assumed p hat is so much bigger than 0.005. All right. Moving on. What if a confidence interval is wrong? Okay. Now, they talk about doing simulations. The 95% confidence interval, you can talk about it two ways. We are 95% confident that the true proportion of whatever is in the confidence interval. Or you can talk about the level of confidence. 95% of all similar samples will yield a confidence interval that contains the true proportion. which means 5%, according to the normal model, 5% of all similar samples will yield a confidence interval that does not contain the true proportion. Okay? So remember, there's always a 5%, you can be 5% confident. If you're 95% confident you're right, you can be 5% confident that you're wrong. All right, what can go wrong? Don't misstate what the interval means. Okay? This is very careful. Don't ever claim that other samples will agree with yours. The bigger the sample size, the bigger the n is, almost for sure you can be certain that the other samples will not agree about you. Don't ever be certain about the parameter. We don't know what the parameter is. Only God knows parameters. That's literally true. Okay? Now, don't forget, it's about the parameter. You're not making any kind of confidence statement about p hat. Okay, you know what your sample statistic is. Make sure that you state that the uncertainty is yours, okay, and not that of the population parameter. Population parameter, it exists, and it's known by a supreme being, but the fact that you don't know it doesn't mean that it's moving around or changing all the time. I mean, it's not from the moment that you're describing it anyway. It is always changing. Okay. Do treat the whole interval likely. Okay, what does that mean? Okay, suppose the confidence interval is, say, 25% and 30%, okay? With the margin of error, obviously, is 2.5%, and p hat would be 27.5%. P hat's right in the middle, and the margin of error is 2.5%. Now, are you more confident that p... Here, let's draw this. Say you have a 95% confidence interval. This is really an important point. Okay, so here's 0.275. That's p hat, right there in the middle. Okay, and then here is 0.25, and here's 0.3. Okay, and in between here is 95%. So here's your 95% confidence interval. Are you more confident that p is in the middle as opposed to in the tails? No. You don't know where p is, and you are not more confident that it is close to 0.25 than to 0.3 than you are that it's near 0.275. Your only confidence is about the entire interval. You are 95% confident that p is in this interval, but you don't know where. And you don't think it's more likely to be somewhere than others. It's extremely important that you realize that. Beware of a margin of error too large to be useful. Okay, remember the cartoon where the guy said it's going to be between -50 and 200 degrees or whatever? That doesn't do anybody any good. Look for violations of assumptions. Random independent, not too big, not too small. Watch the too small thing. They'll trip you up on that. And independence must always be thought about. Okay, what have you learned? Okay, here's all the stuff we talked about. Construct a confidence interval proportion. You now know how to do that. Okay? Margin of error consists of a critical value based on the sampling model times a standard error based on the sample. Okay? Critical value is found from the normal model. Okay, in other words, it's Z star. Standard error of a sample proportion is calculated root p hat q hat over n. You have learned how to interpret it. Okay, this is very, very important. Okay, we've come to understand the relationship of sample size to both certainty and precision. We've learned to check the assumptions. We've learned to find the sample size required. Okay, terminology, standard error, confidence interval. Oops. I don't know. And 1 proportion z interval. Okay, margin of error, critical value. Critical value is the same as z star. Okay, now we're going to talk about on the computer. Okay, that is using statistical software. Confidence intervals, proportions, so easy and natural. Many statistical packages don't offer commands for them. Most statistics programs want the raw data, and then they will produce this for you. Like Excel will do this. For proportions, the raw data are the success and failure status for each case. Usually given a 1 or a 0, but there might be category names like yes or no. Okay. You need to understand and interpret the output, because this could be put into a question for you. So here's the output down here. They got the standard error. Okay, you know what that is. The lower limit, the upper limit, p hat, okay, n, and this is x, the number of successes. This is the population parameter, p. Okay. Here's, they stated the level of confidence, all of this stuff here. So you have to learn how to look at this and interpret it. Let's go through it again. Population parameter, successes, the sample size, n. This is p hat. This is the square root of p hat times q hat over n, the standard error. This is the lower limit, and this is the upper limit. Notice they don't tell you what z star is. Okay. Oops, I went over this. And let's see what's anything on the next page, and there's the homework. That's it.